It's garage chemistry time with Miller. That's me. What up, Lions? Another day, another lab. So today we're going to work on an empirical and molecular formula lab. I like to call it the MgO lab. So I have a piece of magnesium. I'm going to burn the crap out of it. And hopefully it's going to turn into magnesium oxide, which magnesium looks like this beautiful little metal right here. It's going to turn into this like white ashy powder. Once the magnesium oxidizes, it just kind of disintegrates. It turns really brittle because it makes that ionic compound. So you can see a lot of other metals oxidize, like iron rusts, silver tarnishes. So that rust and tarnish is another way we call oxidation. So I'm going to set up my burner right here. I forgot a ring stand, so I'm going to hold the crucible that's going to burn the magnesium over the flame. Hopefully after a couple minutes this thing lights on fire. It's going to look like a flare, so don't look directly at the flame. And then we're going to do some calculations. Otherwise, that's all I have for you. So I weighed out my crucible, I weighed out my lid, and I weighed out my crucible lid and magnesium. And I'm going to show you, because you guys have your lab sheets in front of you, I'm going to show you why we need those specific measurements. And we're going to see what we're going to do with it. Now, you can't see the flame there, but woo, it's going to be hot. So I'm going to put this right over it. And hopefully this thing will light on fire. If not, I have my handy dandy blowtorch that I can torch this thing. Okay? So once it heats up, it's going to start going. Now what we're going to do with these masses here is, since we found the mass of the magnesium we put into this thing, what's happening is as we combust or burn this magnesium, oxygen in the air is going to attach to the magnesium, creating that magnesium oxide and that white powdery substance. What we're going to do is we're going to find the moles of magnesium we put into this and the moles of oxygen that attach to the magnesium to make that magnesium oxide. And hopefully we have a 1-to-1 ratio. Using our ionic formulas, magnesium has a charge of -2, oxygen, or plus +2, oxygen has a charge of -2. So it forms that MgO compound, that 1-to-1 ratio. Let's see if we actually get those results or not. So this reaction usually takes a couple minutes. So I'm going to pause now, and then we'll come back when the stuff actually burns. So literally, like right after I shut that off, it actually started to burn, and it was really, really bright, and the crucible started to crack, so I freaked out a little bit, so I'm glad I stopped it. But I want to show you guys what the product looks like, because I showed you guys the magnesium strip. Here's what the product looks like. So you can see that right here, it's super duper hot. I'm going to point right here. Right here is the magnesium oxide. If I can get a little bit closer, you can see that product in there. Look how gross that is. Nice. And I'm going to let that sit down and cool for a little bit. We're going to let it cool to the touch. Once it cools to the touch, I can weigh it out. If it's hot, as it evaporates, that heat leaving is going to change the mass. So I want to wait till it's cool to the touch to get those masses down. Once I get those, I'm going to show you guys some calculations, and then we're going to call it good. But some fun facts while this cools down a little bit. So I dropped it right on my desktop, so you can see right here. That's a little burn marks for me. Whoops. So it was so hot, the crucible actually, let me show you guys something. Right here, you can see that it's kind of like, the crucible looks like it was like bitten. That's the magnesium that actually melted the porcelain part of that crucible. Cool thing. So it got like super, super hot. That's why when you see the road flares after like accidents or anything like that, or if you put a flare on there, you can kind of see that the road is burnt a little bit. It's because that magnesium reaction is super duper hot. So that's what happened there. All that oxygen hit the magnesium as it heated up, and all those electrons, all those atoms were vibrating really, really fast, and that oxygen kind of fed that reaction, which is how you get that really, really blinding white flame. So that's kind of cool. I'm going to wait for this to cool down. I'm going to weigh it out, and then we'll come back in just a sec. Now, my crucible cooled down enough to weigh it. and I get about 55.26 grams. Now, we started out with just the crucible and the lid with 54.62 grams, magnesium 55.12 grams, so we got a little bit of oxygen. I can already tell my results are going to be way off. We wanted about half a gram of oxygen, so we got about a quarter of that. And I'm going to show you guys kind of what, or I guess a third of that. I'll show you guys what results from that. It's really, really funny and really cool. So let's move on from here. So now that we have those data points, we can get our mass of magnesium. We take the mass of the crucible, lid, and magnesium and subtract just the crucible and the lid. To get the moles, we have to divide by the molar mass of magnesium. And then to get the mass of the combustion product, or the MgO, as I like to call it, you take the final mass, that third data point on there, the 55.26, and subtract just the crucible and the lid. That gets what's actually in the crucible that burned, okay? I get about 0.64 grams for my actual combustion product mass. Now, that leads us to our final thing. How much oxygen did we actually gather from that reaction? Well, take the total combustion mass and subtract just the magnesium from it. That should tell you how much oxygen adhered to the magnesium as it burned. To get the moles of oxygen, divide by oxygen's molar mass. Now, some of you guys are saying, Miller, oxygen's diatomic. Yes, it is. That's for just the oxygen molecule. I'm talking about the oxygen in the combustion product. There should only be one oxygen in there, so that's why it's going to be just 16 for the atomic mass. To get the ratio of Mg and O, we have to use our empirical formula kind of data. So we divide the moles by the smallest number of moles. So we found the moles of the magnesium and the moles of the oxygen. The oxygen moles, the smaller of the two, so we divide each of those moles that we found by oxygen's moles. That'll give us a ratio of 1 for oxygen, obviously, and we get a ratio of 2.35 for magnesium. Now, that's really, really close to 2.33. Since it's not a whole number, it's not like we can round down and say, oh, it's Mg2. That 0.33 carries some weight. So what we're going to do is we're going to multiply it by 3. And what we do to one, we got to do the other. We multiply it by 3 because 2.33 times 3 gets our closest number to a whole, gets it close to a whole number. So it'll get to about 7. Oxygen will get to 3. So we were looking for MgO for our final product. We get Mg7O3. Not very close at all. So probably has to do something with the garage. Probably has to do something with me spilling the product and burning my table. Wish you guys could have seen that. It was absolutely hilarious. Otherwise, there's a lot of other errors in this lab. Think about my conditions. Think about what we're working with. I didn't have my crucible lid on the whole time, so that may have something to do with it. But otherwise, we went through a majority of the questions. Your error analysis, you can figure out. It's supposed to be 1 that we got. So you have to do 1 minus 2.35 divided by 1. So it's going to be a pretty heavy error analysis, like way, way more than 100%. So yeah, otherwise, hope you guys enjoyed. Until next time, we're going to do some mole rockets.